This is video on statics of coplanar non-concurrent forces. This is the second video, and in this video we are going to look at how to find resultant of non-concurrent forces. Now before we actually start, let's have a look at the overall study plan for statics. Statics has two parts: concurrent forces, non-concurrent forces. And in these concurrent forces, there are two parts again: finding resultant, equilibrium. And similarly, in non-concurrent forces also, there are two parts. One is equilibrium problems, and another is finding resultant. In this video, we are going to look at statics, non-concurrent forces, finding resultant. Later videos are going to talk about equilibrium problems and their applications for beams, trusses, and frames. So let's get started, and the best way to start is by way of taking example. So let's say here is an example in which there is a system of coplanar forces. There are 5 of them. Their magnitudes are given and their location as well as direction is given. See, F1, F2, F3, F4 are either horizontal or vertical, and F5 is inclined. But you see, it starts from one end of the this grid square and goes to other end. So you see, angle of inclination is 45. So in other words, information about these forces is completely given. Now our objective is to find resultant of these 5 forces. So method suggested is like this. What you do is you sum up all the x components of forces, call it sigma fx. So what we'll have F1, and then we'll have x component of F5, F5 cos 45. And see, this F2, F3, F4 are vertical, so no horizontal component. So you just have 20, which is magnitude of F1, and F5 cos 45, that is 50 cos 45, and that comes to 55.35 kilonewton. Now you have sigma Fy, which will be summation of vertical forces. So see, F4 is up, so positive, F2, F3 negative, and F5 sin 45 is positive. So if you put the values of F2, F3, F4, you will get sigma Fy 65.35 kilonewton. Now, once you have sigma Fx, sigma Fy, you can find resultant by sigma Fx square plus sigma Fy square under root, and its direction by sigma Fy upon sigma Fx, you take a ratio, that is tan theta, the angle of inclination, and theta comes to 49.74 degree. Now here is the important point. See, what we have done as explained in the first video is we have treated this as concurrent system. So we have imagined actually while writing all this that all these forces are at origin at this point, and we have treated them so far at least as if they were concurrent at origin, which is not really so. So we have to take care of this issue. So what we have essentially done is transfer each of these forces at origin in order to get this result. But while you transfer, as you are aware from the first video of this series, that any transfer of force creates a moment, and it is necessary for us to keep track of these moments. So this equation, the last equation which has come, does that. Let's say the first term. What is this? It is 20 into 3. It is F1 transferred here, so it gives movement of 20 into this perpendicular distance 3. 20 into 3, and the sense is clockwise, and with our convention we have taken clockwise as negative, so this is negative. Similarly, we have done this for every force. For example, F2 50, and distance from origin, the perpendicular distance is 2, 1, 2, so 50 into 2. Then we have taken F3, so that is 20 See, the magnitude is 20 into this distance, 1, 2, 3. So 20 into 3. So that is, again, all these are clockwise sense. So we had put negative sign. Then you have 400. See, magnitude is 100 into 2. This distance is 2, 1, 2. So 100 into 2. So that is, and you see the sign is positive because the sense, you see, about this point of this force moment is anti-clockwise. So we have taken positive. We have sum totaled it. We get minus 20 kilonewton meter, telling us that when I transfer all these forces, the net moment has come as 20 clockwise. And you have to remember that F5 has passed through origin, so you don't need to transfer. That's why F5 has not come in the picture of this equation. So with this information, our answer is this. That is, our resultant consists of one force and one moment. Force is 85.64, which we have got here. And the angle of inclination is 49.74. And the net moment is 20 and it is clockwise. So this is really the complete answer. This is the complete answer. But so to answer it, the resultant of these five forces consists of one force and one moment acting at origin. The magnitude of force and its direction is here, and magnitude of moment and its sense is here. This is really the complete answer. But more professional way of putting this answer is you find distance d by taking ratio of sigma m, that is 20, upon r, that is 0.23. And you move this force, see, you move this force in such a manner by distance d, that is by 0.23, so that it still gives the clockwise moment of 20 about the origin. So what we have done, we have moved this force parallel to itself by a distance d up, so that we get 85.64 into 0.23, which is the ratio of sigma m by r, about the origin, Okay, so these two answers are really equivalent, but this is more professional way of putting it, because then you are answering it only in terms of force. So what it, in other words, what it says is, to this body, which is, let's say, 4 by 4, which is subjected to 5 forces, instead of these 5 forces, you can apply simply this force at this location from the origin, and it will do the same job. So that is another way of answering the question, where you have to just work out this t. So this is how you find resultant of non-concurrent forces. Let's take one more example. Let's say you have all kinds of forces here, so 300, 400, 320, 50, 200, with all its magnitude and the location and the inclinations given. See, all these distances are given, 120, 160. So it is possible to find these angles, like at what inclination is this 400, what inclination is 50, and what inclination is 200. So you have a problem here, and then remember there is a moment, there is a couple here, 4800, and your objective is to find resultant of 1, 2, 3, 4, 5 forces and a moment. So see how we do it. First, we imagine that it has all brought it to origin, and then we simply do sigma fx. That is force by force. 400 cos 53.13. 53.13 will work out as this inclination. Then you have this 50 cos 36.87, both positive because x components come in positive direction. Then minus 320, this one. Then 200 cos 36.87. X component of 200 will be in the negative x direction, so minus. Sum it up, you get minus 200. Similarly, you do sigma fy. That is 400 sine 53.13. 50 sine 36.87, 300, this 300, and 200 sine 36.87. And you get 470, and then you find resultant, and you find this inclination. Great. Now you have to remember that the problem would have ended here if this was concurrent system, but this is not. And therefore, you have to find out what moments have been caused at origin due to all these transfers. And this is done in this equation. See, 320 into 120 is clear. 400, see 400, we have, see along the line you can easily extend the force. So we have taken 400 as if it is acting here. We have done 400 cos 53.13 and multiplied by perpendicular distance 120. There is another component 400 sine 53.13, but that vertical component passes through origin, so it doesn't give any moment, so we are not written in the equation. Then we have 50 cos 36.87, yes, into 120, and then this moment clockwise 4800 negative. We sum total it. It comes out to V0. Fine, no issue. So our result is here. This is the resultant. See, we worked out here 510.78. This is the angle 66.95. Mind you, that the force is in second quadrant for the simple reason that sigma fx is negative in this direction, sigma fy positive in this direction, in vertical direction. So naturally, this has come in the second quadrant, and no moment, because moment comes out algebraically to 0. So this is a complete answer. Thank you.